Hello, this is Dr. Gardner. We're going to be talking about changes in states of matter and performing calculations to determine the transfer of heat energy during changes in states of matter. And this will be an important concept in some of our future laboratories, as well as something that will relate back to specific heat calculations that we did earlier in the course. So first of all, before we look at the calculations, let's consider the processes involved when we're either cooling a sample or heating a sample. Now I can draw what's called a cooling curve as I have a sample that is losing heat energy. And let's imagine that to begin with we have a sample in the gas phase. So we have a lot of empty space between the particles. The particle's kinetic energy is fairly high compared to the other different states that we'll be looking at on this curve. This cooling curve will show as we have the gas cooling. So this first section is when we have a cooling gas, and so the temperature of the gas is dropping as we remove heat from the sample as I go from left to right on this cooling curve. And so we see that as the gas sample cools down, at some point it reaches a temperature that will be the temperature of condensation, which was also the same temperature as your boiling point temperature for this substance. Now, as we go through a phase change, as we go from a gas to a liquid, we'll notice that the temperature is constant here. Now we still are drawing off heat energy, but what's happening is as the gas condenses to a liquid, we end up allowing the intermolecular forces, the attraction between particles, to come in closer proximity. As we do that, that releases energy. So I'm releasing energy during this condensation process as I go from left to right in the same quantity as the heat being removed. So I have a constant temperature as I go through a phase change. Now that's very important. So you want to make a note to yourself. As you go through phase changes for your substances, you expect to usually be ideally under constant temperature. Now when you perform a laboratory experiment related to some of these phase changes, you may notice a process called supercooling, and hopefully your lab instructors will stress that supercooling may occur in that experiment and describe what's going on in that case. But unless we have something like that occurring, we expect that my temperature will be constant as I'm looking at this phase change at the temperature I'm predicting for my boiling point or my condensation temperature. So you'll notice that as we go through this phase change, we get a mixture of the two states of matter that we're changing between. So we'll have the gas phase and the liquid state. So I have a mixture of gas and liquid. As soon as all the gas condenses and all the gas becomes a liquid, at that point, then we're done with the phase change and we're no longer getting additional energy out as the intermolecular forces are coming in closer proximity. And so what we end up having then is we have the liquid state starting to cool, and we'll see a temperature drop again. And as the liquid cools, at some point it reaches its freezing point temperature depending on that liquid. If this was water, that would be 0 degrees Celsius. So at 0 degrees Celsius, water would then start to freeze. Now I go through another phase change as I go through the freezing process. You'll notice this temperature is identical to the temperature you'd have during fusion or melting. We're at that constant temperature during that phase change. And during that phase change, we have a mixture of the two states of matter. So I have a mixture of liquid and solid at that point. As soon as all of your liquid forms a solid state and has more organization between the particles. If it forms a crystalline solid, you have nice long range order between the particles. But as soon as all the liquid becomes a solid, we're done with this phase change here, and then as we have a solid state, we would go ahead and see the temperature begin to drop. So wherever I'm seeing the temperature dropping on this cooling curve, we have one state of matter. Wherever we have a phase change, we have a mixture of the two states of matter that we are converting between. So during this phase change, we have gas and liquid. During the melting and freezing process state change, we have a mixture of my liquid and my solid. Okay. And then where I'm seeing temperature changes, I have gases, liquids, or solids. So that's how I'm reading this cooling curve. Now a heating curve is a very similar process. The only difference is we're still looking at temperature on the y-axis, but the only difference is the heat is being added rather than removed on my x-axis on this graph. So I actually would have a solid heating up, and then as the solid hits its melting point, we would end up going through the fusion process, and I'd have a mixture of the solid and the liquid at that point. And that solid and liquid then, once all of the solid melts to a liquid, we end up with the liquid heating up. And as the liquid heats to its boiling point at this pressure, we'd end up with the evaporation process occurring, and we'll get a mixture during that phase change here of liquid and the gas phase. As soon as all the liquid becomes a gas, we'll see the gas starting to heat up. So that's what we're looking at. But it's very important that you note as we go through phase changes, we're predicting a constant temperature. Now, with this in mind, let's say that you were given a problem where we show you some different forms for the matter you're looking at. So here's A. If we look at A for just a second. So if I'm looking at A here, well, you'll notice this doesn't appear to be a single state of matter. If we look at this diagram, I see some particles have a lot of spaces between them. Their kinetic energy appears to be quite high. So that looks like there's probably the gas phase here. So I expect I have some gas phase particles. But then some of the other particles have, it looks like, a condensed state of matter where they're quite close together, and the disorganization here hints at maybe a liquid state. So it looks like I have an equilibrium process here between the gas and the liquid state, and that would indicate that I probably have a phase change. And so I have to think, on this heating curve, where would I be ending up with a process where I have liquids and gases? Now you would expect that you had begun here with the solid state, heating up the solid until you melted it, and then you ended up with a liquid state, heated up the liquid until you hit its boiling point, and then you ended up the gas phase. Okay, so when I'm reading that, that's what I'm seeing. Now, if I'm seeing a mixture between the gas and the liquid state, that would be this phase change. So if I'm going to the right, what I'm having happen is the liquid is boiling or evaporating, and I'm ending up with the gas. As I go from the right to the left, I end up with the gas condensing and end up with a liquid. In either case, whether I'm talking about evaporation or boiling or a condensation process, we have a mixture at this point of liquid and gas until the phase change finishes. Now that would match what we have drawn here in A. Okay, now if I look at my diagram B here, now in B, I can see that I have condensed states of matter because I don't have the extra spaces between the particles as you expect in the gas phase. So if I'm looking at condensed states of matter, well, the disorganization here on the left-hand side would indicate that I probably have a liquid. On the right-hand side, the organization of the particles would indicate that I probably have the solid state. So this would be what I might see as I'm going through a phase change between a solid to a liquid, since both are present. Okay, if I'm going from left to right on this heating curve, that would be my fusion process, also known as melting. As I go from my right to my left, that would indicate freezing. Okay, in either case, with respect to those phase changes, we'd end up with having a mixture of your solid state plus your liquid state until the phase change has completed. Okay, so that's how I would label these heating curves, as well as how I would identify regions on a cooling curve with respect to the states of matter that are present. Now, let's consider if I want to calculate the heat energy changes as I'm heating up solids, liquids, or gases. So if I have a temperature change and I'm heating a solid, liquid, or a gas, well, we've done those types of calculations before. We've looked at specific heat calculations. Okay, so when I have those temperature changes occurring and I'm actually changing between, or I have a single state of matter that's just heating up but has not changed between states of matter, we use a specific heat equation. Now, to remind you the specific heat equation, well, I'm dealing with Q, that's my heat energy, right? I'm dealing with my heat energy, and that's usually in calories or joules or kilocalories or kilojoules for my units. And then I have my mass, and my mass is usually in grams or kilograms, most likely in grams. And then I have my specific heat constant, which is going to be in calories per gram degrees Celsius or calories per gram Kelvin, or I might have joules per gram degrees Celsius or kilojoules or kilocalories. But the specific heat unit frequently will have a heat unit such as the calories, and a mass of grams usually, and then a temperature unit such as Celsius. Like I said, we might replace Celsius with Kelvin, we might have calories as kilocalories, or we might have joules or kilojoules. Now my change in temperature will be a change in temperature either in degrees Celsius or in Kelvin. Okay, so we've used these calculations previously when we performed the specific heat laboratory where we were identifying unknown metals. We also did some calculations in your homework assignments then. So this is kind of a review there. Now what we have new in this case is not only do we have a single phase of matter going through temperature changes, which I would use this equation for, but I also have phase changes. Now how I know when to use which one of these equations is on a heating curve or a cooling curve. Whenever I see changes in temperature, I use the specific heat equation. If I see a phase change and I have a constant temperature, I would not use this equation because delta T would be 0. Right? There's no change in temperature in those regions. So when I have a phase change, I have constant temperature. So to calculate those, I have to consider a slightly different calculation. I'm going to consider the changes in states of matter having what we call molar heats of fusion or molar heats of vaporization, or we can talk about molar heats of freezing or molar heats of condensation. Okay, so first of all, let's look at what might be occurring with respect to a heating process on a heating curve. And so if I take a solid and heat it up to its melting point and reach that constant temperature relationship, well, the amount of energy it requires to go through that state change will be considered my molar heat of fusion. Now that's where I have that constant temperature on my graph during the melting process. This is the amount of energy it requires to melt 1 mole of a substance. Now that can often be in joules or kilojoules per mole, or we might have calories or kilocalories per mole for our units. Joules or kilojoules are a little more common in these calculations. Now once I have a liquid that heats up until we reach its boiling point, the molar heat of vaporization will be the amount of energy required to evaporate 1 mole of the substance. So you notice in both of these cases we're defining the molar heats as 1 mole, obviously, of the substance that's going through this phase change. Okay, now the units, as I said before, for molar heats of fusion or molar heats of vaporization are usually joules per mole or kilojoules per mole. Okay, and so if I want to calculate the heat energy for a sample to either melt, which is fusion, or go through the vaporization process at the boiling point, we take the number of moles of the sample I have times my molar heat of fusion or molar heat of vaporization as we go through that phase change. So let's look at an example of that. Let's calculate how much energy it might require to boil a sample of water. Okay, so if I take a sample of water, I need to know the mass of the water I'm dealing with. So I need to know the sample size, how many particles do I have, how much water in this case do I have. So I have 125 grams of water, and the boiling point for water, let's say we're at about sea level at about 1 atmosphere, the boiling point of water will be 100 degrees Celsius. Now the molar heat of vaporization, if I look that up, now you don't need to memorize this, I would give this to you on a test, but the molar heat of vaporization of water is 4.07 times 10 to the 4th joules per mole when I look it up. Okay, now remember sometimes it might be listed in kilojoules, so make special note of the units that you have. Now what I'm interested in is just this boiling process. So this heat of vaporization I'm going to consider as I go from water at 100 degrees Celsius to steam at 100 degrees Celsius. So I'm going between the liquid state here to the gas state. And you notice the temperature is constant. Now we expected that on our heating curves, right? As we go through a phase change, we should have a constant temperature. But you'll notice that if I look at water at 100 degrees Celsius and steam at 100 degrees Celsius, there's actually extra energy stored in the steam despite it being at the same temperature. The reason for this is I had to put energy in to remove particles from one another to pull them further apart as they go between the condensed state of matter, the liquid state, to the gas state. Okay, so I did put extra energy in there, which is why you can get a worse burn from steam at 100 degrees Celsius than you could at water at 100 degrees Celsius, because the steam could potentially condense in an exothermic process and give off heat energy to your skin, which would contribute to the burn in that case, more so than just the water, which doesn't have to go through a phase change and would not go through that condensation process. So there is extra energy stored because of the change in state. So let's see how much energy is really stored in this process. How much energy do I put into the water molecules in order to increase their kinetic energy and take them further apart from one another in order to form the gas phase. Okay. Now, the heat of vaporization had units of joules per mole, okay, and if joules is a pretty decent unit for heat, so we're going to go ahead and keep that unit for the heat energy required, but we are interested in canceling out the number of moles. So I need to take the mass of water where you began with. So we started with 125 grams of water. I'm going to convert that to moles by dividing by its molar mass. So there's 18.01 grams of water for every 1 mole of water. So I could go ahead and calculate my number in moles. You can see here we have several moles worth of water. Now, as soon as I have the moles of water, I can take my molar heat of vaporization and multiply by my molar heat of vaporization to get the joules of heat energy I'd have to put in to vaporize this 125 gram sample of water. Okay, so I'd end up calculating 2.82 times 10 to the 5th joules. Now, you'll notice it's a fairly simple calculation. To get this heat energy for our answer, my heat energy that I put into the water sample is equal to the number of moles of the sample. So I'm going to use an N for number of moles, just like we did in the gas laws, right? So I have my number of moles of my sample. You notice I'm using moles and not mass. This is how this differs from the specific heat equation. Then I'm going to use my molar heat of my vaporization process. So I have my molar heat of my vaporization. So I'm going to use an H for enthalpy of my vaporization. So I take that molar heat of vaporization times the number of moles, and that's really as simple as this calculation is to calculate that heat energy. So we had gotten the number of moles here once I converted from grams to moles in order to plug into my calculation. I also had the enthalpy of vaporization that I looked up. Okay, I multiplied those two together to get the heat energy Q here. Okay, and that's as simple as it is for a calculation for a change in state of matter. Now, let's consider, though, if we were looking at some energies of vaporization or fusion. Okay, so let's say we're looking at the fusion of ice. Okay, the fusion of ice is 6.01 kilojoules per mole for the enthalpy of fusion. Okay, now let's consider what would be the relationship here if we were looking at the freezing process. So this is how much energy, 6.01 kilojoules of energy, would have to go into a mole of ice in order to melt it through the fusion process. How much energy would be related to the reverse process, taking a mole of liquid water and freezing it back into a solid. Now you'll notice that enthalpy change, really we have the same change in enthalpy as we reverse this process, because I'm just going from, instead of going from the solid state to the gas state, so let's actually look at a little diagram here with energy. So if I look at energy here, if I'm going between, let's say, a state of matter that is my solid state to the state of matter that is my liquid state here, okay, if I put energy in, that's my molar heat of fusion, and that's 6.01 kilojoules per mole. Now, however, if I go through the freezing process, I'm really just ending up at the original state again. So the difference in energy is identical, but it's just opposite in sign. So if I have this enthalpy for the heat of fusion, if I change the sign, the enthalpy of the freezing process is just a negative 6.01 kilojoules per mole. Right? So all I have to do is change the sign there, and I have the other conversion factor that I might need for changes in states of matter between solids and liquids. Now, if I look at the molar heat of vaporization of water, well, now we're looking at some higher energies here. For the vaporization process, we're going from the liquid to the gas phase. But if I also considered a condensation process going from the gas to a liquid, well, it would just be the reverse process here, just like we saw for the melting versus the freezing. So if I was interested in the molar heat of my condensation process, it's just a negative 40.7 kilojoules. Just change the sign. Okay, so it's as simple as that between converting between these two. Okay. Now, here I have another diagram, and you'll notice we're looking at a cooling curve. As we cool a gas, and then it condenses as I go between the gas and the liquid state, and then I cool a liquid, and then it freezes as I go between the liquid and the solid state, and then I have the solid cooling down. So if this was H2O, we'd have water vapor condensing, then the liquid water cooling, and then I have the liquid water freezing, and then that ice would end up cooling. Okay, so that's my cooling curve for ice. So let's do a calculation related to this. Let's go ahead and remember that as I go through a phase change, okay, with respect to this, I just took the moles of the water times its enthalpy for the phase change. In this case, if I was going through a vaporization process, we had 4.07 times 10 to the fourth joules for that phase change. And so I end up with 2.82 times 10 to the fifth joules. So that's the type of calculation we did when we went through a phase change. But let's consider what's happening as we have changes in temperature. So let's look at region A here, region C, and region E. In those three regions, we have changes in temperature. So I'm going to use a specific heat equation. All right? So regions A, C, and E here all use a specific heat equation. And if I'm looking at H2O in each of these cases, the substance is always going to have the same particles, the water molecules, whether I'm in water vapor, or I have liquid water, or I have the water molecules organized in a solid lattice in the ice. Okay. Now, what differs with this calculation as I have the different states of matter is the specific heat value. The specific heat value is unique to each different state of matter that we're looking at. So if I have water vapor, the specific heat for water vapor is 2.02 joules per gram degrees Celsius. If I have liquid water, my specific heat value is 4.18 joules per gram degrees Celsius. And if I have ice, my specific heat value is 2.03 joules per gram degrees Celsius. So it's a slightly different values that I have depending on the state of matter. So which region I'm in has an identical calculation except for my constant, because there's a different specific heat for every state of matter that we're dealing with. There's a different amount of energy required to raise a gram of that substance by a degree Celsius depending on the state of matter that we have and what's going on with the distances between the particles and their organization. Now, if I consider regions B here and D, as I go through phase changes, there's no change in temperature. So I expect I'm going to use an equation that does not have a delta T in it. So for changes in states of matter, we're going to be dealing with the heat energy change is equal to the number of moles. Now notice here in the specific heat, I was using mass in grams. For the enthalpy changes related to the amount of matter that I have to find the heat energy of phase changes, we're going to use number of moles. So I'm using M versus N here. Now my enthalpy changes are, I would look at my value for my enthalpy of in this cooling curve of my condensation, which is just the negative of my heat of vaporization, right? Or in region D, if I'm looking at a cooling curve and I'm having my sample freeze, I would take the moles of the sample times the enthalpy of my freezing process, which is just the opposite in sign to the enthalpy of the melting, the fusion. So if I'm given vaporization and fusion, I just take the negative sign and I can look at the opposite change in the state of matter as I go through a phase change. Okay, so I really just need two enthalpies of vaporization in order to completely define this graph. Now let's actually use this knowledge to perform a calculation. Let's go ahead and say that we have a sample of H2O, and we're going to convert basically 12 grams of ice. Okay, and the ice is going to be below its freezing point. I can have ice cooler than its freezing point, right, in my freezer. So let's say I have the ice at -5 degrees Celsius. Now I'm going to heat the ice up until it melts, until it goes through its fusion process. And then I'll go through a phase change until all of the solid becomes a liquid. Now once I have the liquid water, I should still be at the same temperature I was at the freezing point, but then I'm going to keep heating the water up to a positive 0.5 degrees Celsius. So I'm going through one change in state here, one phase change, as well as heating up ice and heating up liquid water. So really there's three calculations I need to look at. Okay, so for my very first step here, I'm going to consider warming the ice up until I hit its melting point, which would be 0 degrees Celsius for H2O. Now be careful, because other substances will have different melting points. So you have to know what temperature to reach with that substance before it melts. It'll be unique to every different substance we might work with. So for water, though, it's 0 degrees Celsius. Other substances would be different temperatures. So I go ahead and heat the water up from the -5 degrees Celsius to its melting point of 0 degrees Celsius. And I have to decide what equation to use. Since I have a temperature change occurring here, I want an equation with delta T in it. So I'm going to use my specific heat equation. So my specific heat equation will be the heat energy of this warming process. So as I'm heating the ice up, will be equal to the mass of the ice times its specific heat, and sometimes I'll use an S for specific heat, but sometimes you'll also see a C for specific heat, so don't be confused between that. And then I multiply by my change in temperature, my delta T, as the ice heats up to its melting point. Okay, so as I'm looking at this, I need to make sure that I'm using since I have the solid state for the specific heat for the ice warming up, I need to make sure I use the correct specific heat constant. So my correct specific heat constant here should be the 2.03 joules per gram degree Celsius. So I had to be careful that it matched the state of matter that I was dealing with. Okay, so my change in temperature, though, would be my temperature final minus my temperature initial. My final temperature was the temperature at the melting point for the ice for this first step of my calculation. So that was my 0 degrees Celsius once I reached that melting temperature. My initial temperature was my negative 5 degrees Celsius, so I subtract a negative 5. And so we notice that we should get a positive value here for delta T because the ice is heated up 5 degrees Celsius. So my heat energy change here would be equal to the 12 grams of the sample, right, for the mass, color-coded here for your convenience. I took the specific heat, I made sure it was for solid H2O since that's the state of matter I'm dealing with. The specific heat for ice is 2.03 joules per gram degree Celsius. And then the change in temperature was 5 degrees Celsius as I heat up the sample. Okay, so the heat energy here, we'll notice that my grams should cancel and my degrees Celsius should cancel. So my heat energy here will be expressed in joules. So I end up with having the heat energy here being 121.2 joules. There's 3 significant figures, but I didn't want to round yet because I didn't want to introduce a rounding error. Now this is for step 1 in the calculation. So I calculated the energy required to heat the ice up to its melting point. But I still have 2 more calculations to perform because I still need to consider the ice as it melts. As it goes through that fusion process, I need to know that energy as well. And then I need to calculate the energy as we heat up the liquid water from 0 degrees Celsius to a little above the freezing point or in the melting point to 0.5 degrees Celsius. Okay, so my second step, we're going to go ahead and calculate the change in heat energy for the phase change. Now this is a melting process. Remember, we're calling melting processes also fusion. Okay, so as I look at the fusion process, I'm taking the solid H2O at 0 degrees Celsius, and we're putting energy in until we increase the kinetic energy of the H2O and we start to lose the organization of the solid state. And even though we still have a condensed state of matter, we have a liquid state where there's more freedom of motion. The liquid waters are the H2O molecules are sliding past one another in the liquid state, and so as I go through that phase change, I'll have a mixture between the solid and the liquid, but the temperature will not be changing. Once all the solid ice has melted to liquid H2O water, we end up still having the same temperature, but we've gone through this change in state of matter, and it takes energy to overcome some of those potential energy attractions between the particles to overcome what we call intermolecular forces, which we'll be describing in greater detail soon. Okay, so the equation I should use here, since I do not have a change in temperature, should not be a specific heat equation. It should be my energy related to phase changes using a molar heat of the phase change. Now, since I have, in this case, a melting process, also known as a fusion process, I look up the enthalpy of fusion. So my heat energy here will be equal to the moles of the sample. Now be careful because in the last calculation we used grams. Now we're using moles. So I'm going to have to go ahead and convert from grams to moles to get this calculation started. But then I'm going to multiply the number of moles of H2O by the enthalpy of the fusion process. So my number of moles for H2O will merely be the 12 grams of water divided by its molar mass, 18.02 grams of water for every 1 mole. So that'll give me 0.665 moles of H2O. I didn't round yet because I didn't want to introduce a rounding error with respect to number of significant figures. Okay, now once I have the number of moles, we can go ahead and we have the N value here that I'm plugging in. Right, the 0.6659 moles of water. I'm going to multiply by the enthalpy of fusion. So I went ahead and looked up the enthalpy of fusion as being 6.01 kilojoules per mole. Okay, so I multiply by 6.01 kilojoules per mole, and what I decided to do was to convert this to joules. So 1 kilojoule is 1,000 joules. The reason I'm doing this is because I was dealing with joules on my previous calculation. I need my heat energies, my Q's, to all have the same units before I add them up here in a minute. So I would go ahead and have 6.01 times 10 to the third joules per mole. So I just did a conversion to get from kilojoules to joules. So I multiply by my enthalpy of fusion in joules per mole. My moles will cancel, you'll notice. Okay, and then I'll end up with energy in joules for this melting process. So to melt 12 grams of ice and form liquid water at the same temperature, so at the freezing point, I would have to put in 4 times 10 to the third joules of heat energy. Now I'm not quite done. So far we've looked at the ice heating up from -5 degrees Celsius to 0 degrees Celsius, and I've looked at the melting, the fusion of the ice to form liquid water, but we have not yet heated the liquid water up to 0.5 degrees Celsius. So I have one more calculation to perform. So on step 3, then I'm going to go ahead and warm the water up. And as I warm the water up, we're going to go ahead and have the water warmed from 0 degrees Celsius to 0.5 degrees Celsius. And the equation we would want to use in this case will involve a temperature change. So we'll have a delta T. As I'm heating up liquid water, I will notice that I don't have a change in state of matter right now, so I can use the specific heat equation. But I must be careful because I need to use the specific heat constant here for liquid water, right, not solid when I was dealing with the ice. Okay, so I'm using a different specific heat value. Now remember, sometimes I'll use an S for specific heat. We're using a C here, so you'll see both in some of my notes. So I'm using that for the liquid water right here. So I specifically put a subscript for the state of matter, so I'd remember to use that state of matter here. Now I also will find the change in temperature. Now the temperature final was going to be the 0.5 degrees Celsius. The initial temperature was the 0 degrees Celsius that I had after the phase change. So be very careful not to put in the -5 degrees Celsius. We had already accounted for that when we considered heating the ice up. All right, so we go ahead and put in a 0.5 degrees Celsius minus 0 degrees Celsius. The temperature of the water changes by increasing by a positive 0.5 degrees Celsius as it's heating up. The heat energy change here for Q3 will then be equal to the mass, which is the 12 grams of water, times the specific heat. Since I'm dealing with the liquid state, I make sure I use the specific heat for liquid H2O, so 4.18 joules per gram degrees Celsius, times the change in temperature of a ½ degree increase. And we would see here that the heat energy I put in to heat the liquid water up from 0 degrees Celsius to 0.5 degrees Celsius was about 25 joules. Now to determine the entire heat energy change for all 3 steps, heating the ice, melting the ice, and heating the water, we just add up these 3 heat energy values that we calculated for Q1, Q2, and Q3. Okay? So that's the very last step. We're going to add steps 1 through 3. In other courses, we often refer to this as Hess's Law, as we can add up the enthalpy changes for a multi-step process. So as I add up Q1, 121 joules, okay, that was raising the temperature of the ice as we heated it up until we reached the melting point. And then Q2, as you recall, was when we went through a phase change as we ended up with the solid ice going to liquid water, okay, and then we had a phase change that was the fusion or the melting process. So that was 4 times 10 to the third joule. So that was quite a bit of energy here for the phase change. And then as I heat the liquid water up to end up with having just a higher temperature liquid state sample, we end up heating it up by ½ a degree. That was an extra 25 joules. So as I heat up the ice, go through a phase change, and then heat up the liquid water, I add up those 3 energy changes, Q1, Q2, and Q3, that would give me my total heat energy change for this entire heating process. Okay, and so I end up with having a total energy change of 4.15 times 10 to the third joules. Okay, now should this value be a positive or negative value, I want you to think about that. And what does it tell us? So maybe pause here for a second with the video, and as a class discuss what the sign of the value here tells us. Okay, so if you think about this, whether it should be positive or negative, if it's a positive value for the heat energy change, that would be an endothermic process putting heat into the system, into the H2O sample. If it was a negative value, that would be an exothermic process taking heat energy out. Now this was a heating process. I put energy in to heat up the ice. I put energy in to melt the ice, and I put heat energy in order to heat the liquid water up. So since I'm putting heat energy in, this is endothermic, and the sign should be positive here, so I have the correct sign. Okay, if it was negative, it would be exothermic. That might be occurring like on a cooling curve. Now let's think about what other types of test questions I could give you. Could I give you a test question where not only do you heat up ice and melt the ice and then heat up liquid water, could we heat up the liquid water till we hit its boiling point at that pressure? Sure, we could. If we did that, if we had a more complex problem, as we also ended up with having, let's say, heating my sample up to the liquid water, then this value would have increased, right? Because I would heat up higher than 0.5 degrees Celsius. I would heat up to its boiling point, so this value would have increased. And then I could have had you go through an additional phase change. We could have had a Q4. Now your Q4 would have been your H2O going between the the liquid state, I misspoke, your liquid state to your gas state, all right? And then I could heat up the water vapor, the steam, to a higher temperature than its boiling point. That would be a Q5. So I could have you add up a Q1, Q2, Q3, Q4, and Q5 if you have those additional energy changes to consider. Okay, so I want you to go ahead and practice the homework problems related to this topic. And I would also like you to start reviewing how to draw Lewis structures that we've already covered in the course. With our next discussion, we'll be looking at predicting intermolecular forces, and you need to be able to draw a correct Lewis structure in order to correctly predict those values. Thank you very much.